So last time we were talking about a binomial probability. And we said that the whole point of a binomial probability is that if you have a probability with a certain structure, which is the probability of any number of successes out of another number of trials. And there's a formula that you can use to find the probability. And the formula we talked about was this. And as an example of this, we talked about the example if you have a 5-question multiple choice test and you were to guess on all 5 questions, what's the probability you'll get any 2 questions correct out of 5? So the probability of any 2 correct out of 5 questions because this matches the structure of this binomial probability, that you can use this formula. And if you use the formula, then you're going to get n choose x, which is in this case 5 choose 2. And then p here is defined as the probability of success. Per trial, and success and trial are just generic terms for this general probability. So success just means whatever you're keeping track of. So in this case, because you're keeping track of getting 2 questions correct, that's your success here. So the probability of getting a question correct, that's our P here. What would that be? If we have a 5-question multiple choice test and there's 4 choices per question, A, B, C, or D. Then probability of success would be the probability of getting a single question correct. So that would be
1 out of 4.
Yeah, 1 out of 4, good. So this would be 1 out of 4. Raised to the x power, which is the number of questions that you want correct, which is 2 here, times 1 minus p. So 1 minus 1/4 is 3/4. And then it's raised to the n minus x. So you just take these 2 minus, so 5 minus 2. Yeah, that would be 3. So this simplifies to this. And you notice that we have 3 terms here in our final answer. And we talked about the 3 terms last time. So you can think of this middle term as the success component, because you're just taking the probability of success or getting a question right and raising to the number of successes that you want, and you want 2 correct questions. So this is the success component, and then this last component is the non-success component, where you're taking the probability of non-success or getting a question wrong, because if the probability of getting a question right is 1/4, then the probability of getting a question wrong is 3/4. You're taking the probability of getting a question wrong, and you're raising it to the number of wrong questions that you want to have. If you're to get 2 questions correct, you must get 3 questions wrong out of the 5 questions. So this is the non-success component. And then we have this counting component, because we want any 2 questions to be correct, and the remaining 3 to be wrong. So this is the total number of ways to get 2 questions correct out of 5. So this is the counting component. Okay, and we talked about if you use this formula, then it's really the same thing as thinking about these 3 components in multiplying and multiplying. All right, so this is review of last time. Any questions? Okay, so it turns out that if you look at this formula, you might see a pattern here in the structure, which are, if you take these two probabilities and you add them together, what has to be true? Yeah, they have to add to give 1. You see that in this example, 1/4 plus 3/4 is 1. Or if you take p and you add 1 and you subtract a p out, then you're gonna get 1. So these two probabilities add up to 1. And then what about the exponents? What do you think they should add up to?
Question.
What is it? Yeah, they should add up to the n. So if you look at the example, if you take 2 plus 3, it should adds up to 5, which is the total n that we started out with. But in general, if you take x and you add an n and you remove the x, then these two subtract out and you end up with the total n. Okay, so the exponents in this binomial probability add up to the total number of trials n, and the probabilities add up to 1. Any questions? Okay, so let's talk about what assumptions need to be true for you to be able to use this binomial probability with accuracy. So let's talk about the assumptions. So the main thing is that if you have a probability with this structure, which is a number of successes out of another number of trials. But the fine print are these two assumptions that also have to be met. So the first assumption is that if you look at the name for this concept, it's binomial probability. So the prefix bi means what? Means 2. Okay. So this is part of the assumption, is that we're assuming that there's 2 outcomes per trial. So, for example, in this example, when we had 5 multiple choice questions, each trial was a question that you were answering. So each trial, each question that you're answering had only 2 outcomes. You either get it right or you get it wrong when you guess on it. So there's only 2 outcomes per trial. That's the first assumption. And so you notice that comes from the final result, is that you're multiplying a success component and a non-success component. You're multiplying these 2 outcomes together. And if you had more outcomes, then you couldn't use this binomial probability formula as is, but you could modify it by continuing to multiply the other outcomes by this. So, so let's talk more about this assumption here. So just because there's 2 outcomes per trial doesn't mean that there's 2 total outcomes. It means that there's 2 outcomes that you care about, either success or non-success. So for example, if you roll a standard die with 6 faces, then how many outcomes are there? Every time you roll it, it could be one of how many outcomes? 6 sides, good. So there's 6 outcomes there technically. But that doesn't mean that every time you roll a die, you can't use this binomial probability formula. It depends on the actual probability you're trying to find for that die. So for example, if we're trying to find the probability, so let's say you roll a die, that's 6 sides, and you want to find the probability of rolling a 2 3 times out of 10 rolls, then even though there's technically six outcomes every time you roll this die, there's only really 2 outcomes that you care about, success or non-success. When you roll a 2, that's a success. So every time you roll this die, you're really only keeping track of whether you've rolled a 2 or not. And you want to find this probability that you roll this 2 3 times out of 10. So you can actually get this to having the same structure like we've talked about for a binomial probability. You get it into the probability of a number of successes out of another number of trials. So another way of saying this is that you want the probability of 3 successes, where a success is rolling a 2, out of 10 rolls. So we can get it into this form, and this assumption is technically met because every time you roll it, it's either rolling a 2 or it's not rolling a 2. It's either a success or not a success. So this assumption is now technically met, even though originally there were 6 outcomes per trial. Now there's only 2 that you care about, success or non-success. So technically now you can get it in this form. So let's actually practice using this binomial probability formula now that we've established that you can use this formula. So it would be n choose x, which is what in this case? Yeah, so this would be n choose x, which would be n choose 3, so 10 choose 3, times p to the x. What would p be in this case? Yeah, p would be the probability of a success or the probability of rolling a 2. So that ends up being 1 out of 6 raised to the number of successes we want in this probability. So how many would that be? Yeah, that would be this 3 times 1 minus p, which is the probability of non-success, which is the probability of not rolling a 2.
5 out of 6.
Yeah, that would be 5 out of 6. Or you could calculate it as 1 minus 1/6. And then raised to the number of non-successes we want, or the number of non-2s that we roll. Yeah, so if we want 3 rolls of the 2, then that means out of 10, there's 7 rolls that are not 2s. Okay, so this ends up being the final answer of the probability of rolling 3 2s out of the 10 rolls. Any questions? Alright. So that's that was the first assumption, which is that you need 2 outcomes per trial. Let's look at a counterexample where this assumption is not met. So let's say that you're playing one of those board games where you spin a spinner and it lands on color. And so let's say that the spinner lands on only 1 of 3 colors. So let's say red, green, or blue. And let's say that you spin this spinner 15 times. And you want to know what's the probability that you spin 5 reds, 6 blue, and 9 green out of the 15 spins. Would this be a probability that you can directly use this binomial probability for? Yeah, what is that?
It's 3 outcomes.
Yeah, very good. So first of all, it doesn't even really fit the structure that we've been talking about. It's the probability of a number of successes out of another number of trials, because of these three, there's no one that you can call a success where the other ones are non-successes. You can't just call the 5 red and then collapse the blue and the green into 15 and call the 15 non-successes, because you have to specifically keep track of 6 blue and 9 green. So there's no one that you can call success so that the remaining are just simply non-successes. You have to keep track of all 3. And this assumption now is then not met. Because now you have to keep track of 3 things each time you spin the spin. So this would not be binomial. So this is not a binomial probability. And because it's not a binomial probability, you can't just use this formula as is without doing any modification. If you wanted to use this, you would have to modify it. Otherwise, you'd get an answer that was not accurate. So in this class, you're not responsible for finding this type of probability that is not binomial. Technically, this is a trinomial probability because there's 3 outcomes per trial. Or more generally, it's a multinomial probability. So this is a trinomial, or more generally, a multinomial probability. So in this class, you're not responsible for finding the answer to this. You're just responsible for saying, hey, this isn't binomial. And that's sufficient for this class. But that said, to actually find that answer, all you would have to do is modify this binomial probability slightly, and you'd be able to come up with that answer. In this class, we're not going to talk about it, but if you see me after class, I'll be happy to talk with you about it. But you might want to just think about on your own, just so that you can understand this concept even more. How might you modify this binomial probability so that you can get this answer? Let's talk about it a little bit. So right now there's this success component and a non-success component. There's only 2 outcomes listed. So if you want to include the 3rd component, then you would continue to multiply the probability of getting this 3rd outcome, like green, for example. You would multiply the probability of green, which in this case is, if there's these 3 regions, let's say, that are equal areas, then it would be 1 out of the 3 for the probability of green. So you would multiply an extra outcome here. The probability would be 1 out of 3, and then raise to the number of green that you would want in this case, which is 9. So that's all you would do, is multiply this extra component of green, 1/3 raised to the 9th. But then you would have to modify this counting component. So that's a little bit trickier, but for now, we'll just leave it like that. You would need to modify this correct counting component, and then that would give you the correct probability. But think about how you might modify that. How would you find the total number of ways that you can get 5 red, 6 blue, and 9 green out of 15 things? And you actually have the tools to be able to do this. It just happens to be outside the scope of this class. But think about it, and if you're curious, if you can't sleep at night because you want to know the answer, then feel free to see me. Okay, so so for this question, it's sufficient just to say that this is not binomial, this is multinomial. But what if I modify this only slightly and said, okay, what's the probability of 5 red and the remainder is blue-green. So there's going to be 15 that are either blue or green out of the 15 space. Out of the so the remainder out of the 20 space, or no. So yeah, so these numbers aren't adding up. So let's say that I spin it 20 times, and then I'm getting these So out of these 20 spins, I want 5 red and the remainder, which are the 15, to be what's left over, which is blue green. Okay, so the question is, would this be binomial? Could I use the binomial probability formula here for this example?
Yes.
Yeah, so why is that? Because each time you spin it, yeah.
It's because the blue-green is like everything else, so you can like separate it to one of two things, like success or non-success.
Yeah, excellent. So every time you spin it now, you only have to keep track of whether it's red or a success. And if it's not red, then it's blue/green, and it's considered a non-success. So now you only have to keep track of whether it's a success or a non-success, red or not red. So in that case, because this is a binomial probability that you can use this binomial probability formula for, let's go ahead and, as practice, find this probability together. So we're going to find this probability of 5 red and the remainder 15 to be blue-green out of the 20 spins. So the first thing is, we might want to get into the structure that we're used to for describing a binomial probability, which is the probability of a number of successes out of another number of trials. So the only thing here is, what do we call a success? Do we call red a success, or do we call blue-green a success?
Right.
So it turns out that it doesn't matter. So it's arbitrary, just whatever you're keeping track of. You just need to be clear on what a success means to you. So let's go ahead and separate it out into two cases. One where a success is red, and one where a success is blue-green. And this is to show that you're going to get the same answer for the probability at the end. We're going to do it both ways, and to verify that we're going to get the same answer at the end. So if the success is red, we're just going to write the probability as a probability of 5 red out of 20 spins. And if a success is blue-green, then we're just going to say the probability of 15 blue-green out of 20 spins. Okay, and let's find both probabilities and verify that we're getting the same answer. So for the first probability, we're just going to use this binomial probability formula, and the first term is going to be n choose x. So what will that be here? Yeah, 20 choose 5 times the probability of success. In this case, success is red. So the probability of red raised to the number of red that we want. So if we have this spinner, which has, these are equal areas, and red is one of the areas, then it would be 1/3. So the probability of red will be 1/3 raised to the number of red spins that we want here, which is 5, times the probability of non-success, or not red. So what's the probability of not being red here when you spin it?
2/3.
Yeah, 2/3. Good. Raised to the number that aren't red that we want here out of the 20 spins. Yeah, 15. Okay, so this would be the expression if we deem a success as being red. So let's do the other case. So now we're deeming blue-green as being a success. So if we do n choose x here, what would that be? Yeah, 20 choose 15. Raised to the number of, probability of success raised to the number of successes. So success here is blue-green, so what's the probability of success here? Yeah, it would be 2/3. And then this is being raised to the number of blue-green we want, which is 15. Always 15, and then times the probability of non-success, which in this case is not blue-green or red.
1/3.
Which is 1/3. Raised to the number of non-successes or reds that we want.
5.
Yeah, which is 5. So, if you compare these two expressions, you basically have three quantities that are being multiplied together. And you know that if you multiply numbers together, it doesn't matter the order in which you multiply numbers. So, on this side, there's a 1/3 to the 5th. And on the other side, there's also a 1/3 to the 5th. And on the left, there's a 2/3 to the 15. And on the other side, there's also a 2/3 to the 15. But the only difference is on one side, there's a 20 choose 5, but on the other side, there's a 20 choose 15. So go ahead and punch those numbers in your calculator. What is it?
0.145.
No, for now, just type in 20 choose 15 just by itself.
Okay, like that.
It's the same.
Yeah, it turns out that they're the same number. If you type in 20 choose 15 or 20 choose 5, it turns out they're the same number. And the question is that a coincidence? So why is that? So let me take a little detour for a little bit and talk about why 20 choose 15 is the same as 20 choose 5. So you remember when we talked about the first example of this yesterday, when we talked about 5-question multiple choice tests and writing out all the possibilities of getting any 2 correct out of 5. So when we wrote those out, we said, for example, getting the first and second questions correct was one way that you could get 2 questions correct out of 5. And then any numbers that we didn't list, that implied that we got those questions numbers wrong. So we're getting question numbers 1 and 2 correct, but getting questions 3, 4, and 5 wrong. So this implies this situation. Another way is if we get questions 1 and 3 correct, that would imply this situation. 1 and 3 are correct, but the remaining are wrong, and so forth. So we wrote out all these possibilities. Then we said that how many possibilities do there end up being? Yeah, so if we have 5 questions total, and we're keeping track of the questions that we get correct, this is choosing 2 correct numbers out of 5 total, where the order of the 2 correct doesn't matter. So another way of saying this is 5 choose 2. That ended up being 10. So there's 10 total possibilities here, corresponding to getting 2 questions correct out of 5. But here you notice that we indicated the situation of getting the first 2 questions correct simply by listing out the question numbers that we got correct, 1 and 2. But could we have also represented the situation as keeping track of the 3 questions that we got wrong?
Yeah.
So we could have kept track of the same situation as, I'll say versus. Now we're gonna keep track of the 3 questions we got wrong, 3, 4, 5. And on this one, we'll also keep track of the 3 questions we got wrong. So this one would be 2, 4, 5, and so on. So if we keep track of the 2 questions we get correct out of 5 questions, then there's 10 possibilities total. That ends up being 5, choose 2, which is 10. But what if we kept track of the 3 questions we got wrong out of 5? How many should there be?
The same.
There should be the same number, because every possibility out of these 10 has exactly one analog corresponding to the questions that we got wrong. So here, if we keep track of the 3 questions we get wrong out of 5 questions, there's going to be 10 also. But what's the expression that represents these 10? It's going to be 5 choosing 3 numbers. So this will be 5 choose 3. So in both cases, you're getting 10. You're getting the same answer. And what these share in common is that this 5 is the total number of numbers. This 2 and 3 are the numbers that you're choosing from. But the 2 and the 3 add up to the total of 5. So if you have 5 choose 2, that's going to be the same as 5 choose whatever number adds up with 2 to give 5, and that's going to be 3. So 5 choose 2 is the same as 5 choose 3, and likewise, if you had 20 choose 5, that's the same as 20 choose 15, because this 5 and this 15 adds up to the 20. Right, so it's not a coincidence. So likewise, if we had 100 choose 20, that's the same as 100 choose what?
80.
80, very good. So that's always going to be true. And you can verify that on your calculator. Any questions? So the point is that, back to this example, now we're back on the detour. If we have this probability we're trying to find, it doesn't matter what we label as our success. The success is just whatever we're keeping track of out of the 2 outcomes. So we can either deem success as being red, or what's left over, blue-green, and we're gonna get the same result for the probability. And this is a good illustration also to show that success doesn't have a positive connotation to it. Success is just whatever we're keeping track of. Okay, any questions? All right. So that was the first assumption. The first assumption is that you have 2 outcomes per trial that you can label as either success or non-success for each trial. And so let's talk about the second assumption that has to be true. So you notice that each of these binomial probabilities that we talked about, that came from the binomial probability formula. For success, for the success component, for example, you have the same probability of success, 1/3, and you're going to multiply that same probability over and over, this number of times, 5 times in this case. This probability doesn't change. So another way that we've said that in the past was that the probability of success is independent. And what that meant was that if you had a success in one trial, for example, if you spun a red in one spin, then it doesn't change the likelihood of spinning red in another spin. So they're independent of each other. That's why you can use the same probability over and over. So again, this formula only works if each trial is independent from the other trials. And we saw in the past that's not always the case. Sometimes something happening might affect the likelihood of it happening in the future, in which case they would not be independent. So the second assumption here is that if you have a success in one trial, it doesn't change the probability of success in a future trial. So, success in one trial does not affect the probability of success in a future trial. So that's the more intuitive explanation, but the mathematical explanation is that the trials are independent of each other. So another way of saying this is that the trials are independent. So again, all that means is that if you look in this formula that we end up using the same probability of success or the probability of non-success over and over again by just raising it to a power. If they were different, we'd have to multiply all these probabilities that are different in succession. But this formula, we don't do that. We're using the same number multiplied by itself this number of times. Yeah.
Can you reread that bottom part? I can't see.
Oh, sure. This says, success in a trial does not affect the probability of the success in a future trial. And the mathematical way of saying that is that the trials are independent.
The problem says that it is without replacement. Does that mean that it is not independent?
Yeah, so technically without replacement means that it's not independent. But then remember we talked about the 5% rule, where technically even if it's not independent, you can treat it as independent in certain cases if the sample size is less than 5% of the population size. And we'll review that. But good question. So let's look at an example. Let's say that you have a company with 50 employees. And let's say that every year a fixed percentage get raises. So 20% of employees get raises. So that means out of 50 people, how many would get raises?
10.
Yeah. In this company, it would mean 10 get raises. So let's say that you select 10 employees. What's the probability that 7 will get raises? From the 10 that you select. So first of all, the probability of the situation you're trying to find, does it have the same structure as a binomial probability? Probability of a number of successes out of a number of trials. Yeah, so it's a probability of a number of successes where getting a raise is a success out of another number of trials, or one trial is one employee. So it seems to fit the structure, but now to make sure that we can use this formula as is, we have to check to see whether the assumptions are true. So are there two outcomes per trial? So for each employee, are there two outcomes?
Yeah.
Either success or non-success. Yeah, so either they get a raise or they don't get a raise. So that would be a success or a non-success. So the first assumption is actually met. And so now let's test the second assumption. The second assumption is if one employee gets a raise, does that affect the probability that a future employee will get a raise?
Yeah.
Okay, so why is that?
Because there's one less to give out, there's no replacement.
Yeah, very good, very good. So you know that there's only 10 people getting raises total. And so if one employee gets a raise, now there's one less employee that's possible to get a raise. And so, that person getting a raise affected, the probability for the next person to get a raise. So for example, if, what's the probability that the first employee that you select gets a raise?
1 out of 5.
Yeah, okay. So that ends up being it's gonna be the 10 people out of the 50, and that simplifies to 1 out of 5. So that's the probability that the first person that you look at ends up getting a raise. But now let's assume that they got a raise. So to be consistent with the notation we've been using, given that the first gets a raise, what's the probability that the next person will get a raise or the second person gets a raise?
9 out of 49.
Yeah, very good. So if the first person indeed got a raise, there's now one less person who got a raise. So instead of 10 people, now there's 9 out of the total 49. So now the probability is 9 out of 49. And these probabilities are now different from each other. So these events are not independent, these events are dependent. So whether the second person gets a raise is dependent on whether the first person gets a raise, because this conditional probability is different from this non-conditional probability. So these events affected each other. So because of that, we can't use this binomial probability as is, because the probability of success now changes throughout. You can't just use the same number and raise it to a pound. So, if this question was originally asked of you, you would just say that this is not binomial. Any questions? Okay, so let's say that this question is modified just slightly. And instead of a company with 50 employees, let's say that there's 500 employees. But let's say everything else is the same in that 20% get raises. But if 20% get raises, the actual number of people who end up getting raises will be a different number. So if 20% get raises, how many number of people get raises?
100.
Yeah, so it'll be 20% of 500, which is 100. But now you also select 10 employees and ask the same question: what's the probability that 7 will get raises out of the 100 employees? So I'm gonna ask that down here. So what's the probability that 7 get raises out of 10? Out of the 10 that you select. Okay, so is this probability binomial? Where you could use this binomial probability formula as is. So first of all, let's check to see whether it fits the main structure. So the main structure is this situation, the probability of a number of successes out of another number of trials. Yeah, so this probability fits that structure. And then we're gonna test the assumptions now, one by one. So the assumptions are there 2 outcomes per trial, either success or non-success for each person? Yeah, so each person either gets a raise or doesn't get a raise. So the first assumption of two outcomes is met. The second assumption is independence. So is the probability of success constant throughout? So if one person gets a raise, does that affect the probability that the next person will get a raise? So technically it does, but remember, we talked about the 5% rule in the past, where even though technically the numbers are different, if they're close enough to each other, then you can treat them as being independent of each other. So in this case, what's the probability that the first person will get a raise? It'll be 100 out of 500. And what's the probability, assuming the first person gets a raise, what's the probability that the next person will get a raise? So now it'll be 1 subtracted from both the top and the bottom, so it'll be 99 out of 499. So intuitively, do you think these final fractions will be close enough together where you can effectively just use the same number and not lose much accuracy? Yeah. So these numbers end up being very similar in value. So because of that, even though technically they're different, we can use the same value and not lose much accuracy. So we can treat them as independent, even though they're not. But we can use a rule that quantifies this, and we've talked about this, this is called the 5% rule. So the 5% rule, recall, says that if the sample size is less than 5% of the population size, if it's much less than the population size, but we can quantify that with only less than 5%. So if the sample size is less than or equal to 5% of the population size, then we can treat the draws of the sample as being independent of each other, and we can use the same probability of success over and over again. So in this case, let's go ahead and use this 5% rule. What's the sample size, what's the population size? So the sample size is the number that you actually select. In this case, it's 10. So the sample size here is 10. And the population size is everybody. And that's 500. So is 10 less than 5% of 500? Yeah, so 10% of 500 is 50, so 5% is half of 10%. That turns out to be 25. So 5% of 500 is 25. So 10 is definitely less than 25. So because of that, the sample size is a lot less than the population size. So you can use, you can treat these as being the same probabilities. So because of that, we can assume this independence assumption on the second assumption. And we can assume independence, so we can go ahead and use this formula. So let's practice. So we want to find the probability that 7 get raises out of 10. So let's, now that we said we can use this binomial probability formula, the first term will be n choose x. So what's that going to be here?
10 choose.
Yeah, 10 choose 7 times the probability of success. In this case, success is what we're keeping track of, which is getting a raise. So what's the probability of getting a raise?
1/5.
Yeah, either you can say 20% or you can say 100 out of 500, same thing, but we're assuming now that that probability stays fixed throughout all the employees. So that's going to be 20% or 1/5 or 100 out of 500, but let's say 0.2. And that's the probability of getting a raise, and then raise to the number of people that we want raises.
7.
Yeah, that's going to be 7 here. And then times the probability of non-success or not getting a raise, 0.8. Raise to the number of people who don't want to get raises out of 10. 10 minus 7, which is 3. Yep. Alright, great. So that would be the answer to this probability. Any questions?
Sorry, I was throwing down. Where do we get the definition?
Oh, so yeah, this is 20%, this represents the probability of getting a raise.
Oh, okay.
So that was up here, 20% get raises.
Alright, thank you.
Yep. Alright, so what we just did then was we talked about when we can use this binomial probability, which is when it fits the structure, a probability of a number of successes over another number of trials. And then we also have to check the fine print. The fine print is that you have 2 outcomes per trial. If you have more than that, it's not binomial, it's multinomial. And then the second assumption is that the trials are independent, which means the probability of success is constant throughout, and likewise the probability of non-success is constant throughout all the trials. Any questions? All right, so let's do some more practice. Let's say that you take a multiple choice test now that is 30 questions. And let's say that you have 4 choices for each question. You could either fill out A, B, C, or D for each question. Let's say that passing this test means that you get 20 or more questions correct. So if you were to guess on all 30 questions, the question is, what's the probability of passing? So let's step through this together. So the probability of passing means that you have to get 20 or more questions correct. So you want the probability of 20 correct or more. 20, I'll just say 20 or more correct. Out of 30 questions. So, can we just use the binomial probability formula here?
No,
Okay, so I know.
because, there's like a range of success, not just one specific.
Okay, excellent. Because here, this is the probability of a single number of successes out of another number of trials. But here we have a range of a number of successes, right? We have 20 or 21 or 22, all the way up to 30. But this is something that we might have seen before that we might be able to deal with, which is we have a probability with events drawn by or here. So which mathematical rule is that? Yeah, that was the addition rule. So now you can split this up into separate probabilities that you can add up. So this is the probability of getting either 20 correct out of 30, or getting 21 questions correct, which means that you can add the probability of just getting 21 correct out of 30. Plus the probability of getting 22 correct out of 30, and so forth, all the way up to 30. And then technically, in the addition rule, there's a subtraction component where you're subtracting out the overlap between possible events. So for example, you want the probability of getting both 20 correct and 21 correct in the same test. But what should that probability of overlap end up being? Yeah, 0, why?
You can't get 21 and 22 correct at the same time.
Correct, very good. So in the same test, on the same event, you can't have these overlapping situations. You can't both get 20 questions correct and 21 questions correct on the same test. So because of that, you don't have to worry about subtracting out the overlap, because that probability will be 0, because they're disjoint, mutually exclusive events. So the addition rule then is just adding up these separate probabilities, and there's no subtraction. So if you wanted to correctly find this answer, you would have to add up all these probabilities from 20 to 30. And how would you find each individual probability?
Plug it into the binomial.
Yeah, very good. So each individual probability is a binomial probability that you find from this formula. Because the probability of this number of successes out of this number of trials, so it fits the structure. And also, both these assumptions are met, because there's 2 outcomes per trial, success and non-success. You either get a question correct or not correct when you answer it. And then the second assumption, if you get a question right, it doesn't change the probability that you get another question right. So the probability of success or getting a question correct is constant throughout all the questions. So both assumptions are met. So you can use the binomial probability formula for each probability here from 20 to 30, and then you would just add all these up. But right now, I just want you to know that that's what you're supposed to do. I'm not going to physically require you to apply this formula 11 times and add them all up to get an answer on the test. But right now, I need you to know that this is what you need to do. So apply this binomial probability formula for each probability and then add them all up. Any questions so far? And then later on, you'll see, right now we're in chapter 5, but later on in chapter 6, you'll see that there's going to be a shortcut to, if you find yourself adding up these multiple binomial probabilities, there's going to be a shortcut that we talk about where you can address this without having to add these up.